Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover undetermined coefficients, and in particular, the annihilator approach. And I'm going to introduce what it means to be differential operators. So let's start out with something that we're familiar with. A second-order linear homogeneous differential equation, and I know I can solve this using the characteristic equation. So this is going to give us an r squared plus 4r plus 3 is equal to 0, and I know when I factor this characteristic equation, the zeros of the characteristic equation is going to help us find some coefficients that are in the solution to the differential equation. So let's look at the differential operators. So I'm going to rewrite this as, y double prime is going to be d2y plus 4 the first derivative of y, and then plus 3 just y is equal to 0. So you can see that what I'm doing is d2 is representing the second derivative, the second derivative of y, so that's why we call it operating. This is operating on the function for the differential operator of y, and then 3y. Now, these differential operators algebraically act a lot like multiplication, so what I can do is I can factor out this y, so d squared plus 4d plus 3y. So technically it's this of this, but it happens to look a lot like multiplication, doesn't it? So we can see that, boy, this looks familiar. This looks like the exact same coefficients as the characteristic equation, and it sure is. So that means it'll also factor identically to the characteristic equation is equal to 0. So once I have these differential operators are equal to 0, or the characteristic equation is equal to 0, we know that these coefficients will work with the solutions to the differential equation. So our solution is going to be equal to, well, we know that I have zeros here. This is going to be, we'll say r is equal to -3 and r is equal to -1. Or I can also see the -3 and -1. So this is going to be like some c1e to the minus 3x plus c2e to the minus x. And it's, this solution is the full solution because this is a homogeneous differential equation. So really the idea is what happens when this is not a homogeneous differential equation, and how can I find coefficients of these differential operators to really kind of expand the solution. And if it's not homogeneous, we know that we're going to have, a characteristic equation, well, not characteristic, a complementary, and then also, the particular, which is going to be for that non-homogeneous part. So this first video is really going to show you how to annihilate this non-homogeneous part, and then I'll do a part 2 to where we find solutions of the differential equations using those annihilation operators. So let's find these differential operators that annihilate. So the differential operator that annihilates each one of these functions, really we're kind of looking at polynomials of degree. In this case is going to be n minus 1. So this is 1x to the 0, this is x to the 1, this is x squared, and so on. So the differential operator that annihilates these things is going to be this power on d is going to be 1 more than this power on x. So for instance, if I want to know, if I do a differential operator on just k, where k is a constant, where I know is the derivative of a constant is equal to 0. Similarly, if I take the derivative, the second derivative of x, I know that, remember this would be x to the 1, so that means I'm using n equals 1. This should just be, I have to use 1 bigger than this. So the second derivative of x is going to be the derivative of the first derivative of x. So the first derivative of x is going to be equal to just 1, so this is the derivative of 1, and we know the derivative of constants is equal to 0. So you can see that the second derivative annihilates x. Very similarly, what if I have the third derivative of, say, x squared? The the power on d has to be 1 bigger than this 2. So this is going to be the derivative of the derivative of the derivative of x squared. And, working through this, we know that this is going to be, well, the derivative of 2x. And then we have the derivative of 2x, which is going to be, so this will be, this became here. And then finally, I'm going to have to take this thing's derivative. So this is going to be the derivative of just 2, which is equal to 0. So finally, let's kind of ask a question like, what annihilates, say, ax to the 7th? So we're not going to go all through all the work, but what's going to annihilate this x to the 7th? It's going to be d of the power 1 bigger than that 7. So the 8th derivative of x to the 7 is going to be equal to 0. Or what if I ask, like, what annihilates, like, 4x to the 5th? Do constants matter? No. If I take the derivative, so this is going to be the derivative to the 6th power of this thing. So what I know is I can pull out the 4 if I want to, and then the 6th derivative of x to the 5th will be equal to 0, and 4 times 0 will be equal to 0. So again, this will be equal to 0. And then finally, what if I have a 5x to the 4th minus 2x squared plus 4x minus 17? What if I have a polynomial that is degree 4? Well, what we go after is the highest power. I need to annihilate this. So the derivative that's going to annihilate this is certainly going to annihilate all the powers less than this. So I'm going to need a d. Well, I have to go 1 bigger than the 4. So this is going to be 5 of this expression. And we can double check it by doing this method here, but we can see that this will clearly be equal to 0. What about other families? So what annihilates each one of these? Well, more importantly, this is kind of the general expression that annihilates it. So if I have x to the n minus 1 e to the alpha x, then this is going to annihilate these things. So, these things take the exact same form. So let's just kind of verify that it annihilates, say, this one. And then I'll kind of explain why it does the inverse. So let's do something of this form. So what if I have a x e to the, say, 5x, for instance, and I want to annihilate that? Well, what I can see is that this is an x to the power of 1 e to the 5x. So this power, very similar to what we had with the polynomials, needs to be 1 bigger than this 1, so the n is going to be equal to 2, and then alpha is going to match that coefficient of 5. So what I'm going to need is I'm going to need a d minus 5 squared is going to annihilate this. So I can expand this, so this is going to be, this is d squared minus 10d plus 25, and all I did is FOIL a binomial, x e to the 5x. And then I'll distribute this through, or really compose it through all of these differential operators. So this is now going to be equal to the second derivative of x e to the 5x minus 10 times the first derivative of x e to the 5x and plus 25 x e to the 5x. And then, like I said, I'm going to verify that this will give us 0 because that's what it's supposed to do. Well, I have to take the second derivative of this expression. So this is going to be equal to the first derivative of, well, the derivative of this expression. And since this is a product, I have to use the product rule. So the first derivative of this, derivative of the first, is going to be 1 times the second. So I'm going to have an e to the 5x plus the first, which is going to be an x. And then the derivative of the second, which will be e to the 5x times 5. So 5e to the 5x minus 10 derivative of x e to the 5x, and then finally plus our 25x e to the 5x. And now I'll do all these first derivatives next. So now the derivative of this thing, well, this is the derivative of e to the 5x is 5e to the 5x. The derivative of this is, again, another product rule, so derivative of the first times the second plus the first, which is going to be a 5x, times the derivative of the second, so 5 times 5 will be 25e to the 5x. And then finally we have minus 10. The derivative of this, again, a product rule, so derivative of the first, which is 1, times the second, plus the first times the derivative of the second. And then finally plus our 25xe to the 5x. So simplifying this is 5e to the 5x. I know I could add this to 10, but we will just expand and then cancel. Because remember, this is supposed to be equal to 0. We're just double checking that. So this will be a minus 10e to the 5x, minus 50xe to the 5x, and finally plus 25xe to the 5x. And does this equal 0? Well, all right. I got a plus 10e to the 5x. I got a minus 10e to the 5x. That's done. I have a negative 50e to the 5x, and I got a positive 50e to the 5x. So this indeed is equal to 0. So this is working. All right, so just without verifying it, what if I have, what if I want to annihilate, say, a 7 x to the 4th e to the minus 3x? What if I want to annihilate that thing? Remember, it's of this form. The coefficient 7 doesn't matter. You can always pull a constant. So whatever makes this 0 will make this thing 0 as well. So what is the power on n? Well, this has to be 1 bigger than the power on x. So I'm going to need this thing to be to the 5th power. And this is going to be a d, minus, and then this alpha is going to be the coefficient of this right here, this negative 3, so minus a minus 3. So you can verify it. It'll take a minute, but this does annihilate this. This will be equal to 0. To kind of give a hint what's going on, remember that these things have zeros, and the zeros of these differential operators are related to the solutions in the differential equation. So you can see that this has a repeated root of 0, and this has of 5, and this has a repeated root of negative 3. So we'll see in the next video that we're going to use these zeros to find some solutions. So I want to determine the differential operator that annihilates this. Now what I can see is that this thing is built of, well, the first example, which had to do with polynomials, and the second example, which had to do with, the product of polynomials and exponentials. So if I had this piece right here, if I want to do my x squared minus 3x plus 1, what annihilates that thing is going to be, d to 1 bigger than this power. So this is going to be d cubed. That'll be equal to 0. And then very similarly, if I want to annihilate this xe to the 7x, well, this is, a binomial to a particular power, my d minus. Now, the power is going to be 1 more than the power on x, so this is going to be a squared. And then this is going to be a minus whatever the coefficient here, which is going to be equal to 7. So what happens if you have a combination of these things? Well, you have to use both of them. So what if I take my d... If I take d cubed and also the d minus 7 squared of this expression, my 5x squared minus 3x plus 1, this will indeed equal 0 because this of our 5x squared minus 3x plus 1 plus xe to the 7x. This will indeed equal 0 because, this annihilates this polynomial, and this annihilates the exponential. Right. One more family and then a special case of that. So the differential operator that annihilates exponentials and trig functions together, so e alpha x cosine beta x or e to the alpha x sine beta x. And then also when we introduced your polynomial in front, so in general, like x to the n minus 1 e to the alpha x cosine beta x, or x to the n minus 1 e to the alpha x sine beta x is going to be equal to this differential operator. So you can see your alpha being here, your beta being here, and then your n being 1 bigger than the power on that polynomial like before. So if I want to find the differential operator that annihilates this, I'm going to rewrite this in such a way I can see that x. I really want to see that power on x because I know this n has to be 1 bigger than that power. So the differential operator that's going to annihilate this is going to be, you know, this thing with the appropriate alpha and the beta. So this is going to be our d squared minus 2. Well, alpha is going to be the coefficient in that exponential, so it's going to be a -1 d plus, we have our alpha, so this is -1 squared plus, now the beta is going to be the coefficient that's in your angles, so this is going to be 2 squared. And this is all to a power that is 1 bigger than the, you know, the power on x, so this is going to be 1. So if I want to, you know, simplify this, this blue, I'm not going to do brackets, let's do parentheses. So I have d squared plus 2d, and then 1 squared, -1 squared is 1, plus 4 is going to be 5, so plus 5, all to the first power, you know, operating on my, you know, my 5 e to the negative x, cosine of 2x minus 9 e to the negative x, sine of 2x, and then, you know, with a little bit of verification, and actually it's not too hard with these, you'll see that you'll get 0 back. It's very similar to what we did with the exponentials and the polynomials. So again, there's a part 2 to where I use these annihilators in order to solve differential equations. So if you like the content, please subscribe and join next time.